8.3 Areas and Tangents. A tangent line is a line that goes through only one point on a curved graph. Without crossing over. For example, on this curved graph, if we pick any point, let's call it point A, a straight line that goes through point A without crossing over the graph or going through any other point is called tangent to point A on that curved graph. Areas. For this lesson, you're also going to be able to need to calculate areas of basic shapes, including the area of a rectangle defined by length and width. The area of a rectangle is equal to length times width. You'll also be able to need to calculate the area of a triangle, which has height h and base b. The area of a triangle is 1/2 base times height. These two formulas will be useful in a little while. First, we're going to look at what tangent lines mean to a displacement as a function of time graph, a d versus t graph. Here's an example of a simple d versus t graph. A linear-shaped graph on a d versus t graph means we have constant velocity. The slope of this linear line is equal to the velocity. A curved graph, we've learned in previous lessons, is a quadratic graph. And this quadratic-shaped graph means velocity is changing, or we have constant acceleration. You can still find the velocity on this curved graph by plotting a tangent line to whatever point we're interested in. You can find the velocity at a particular instant in time by finding the slope of the tangent line to the curve at this point. So for the tangent that I've drawn onto this graph here, we can find the velocity at that instant in time. We call this velocity a particular instant the instantaneous velocity. And you can find this instantaneous velocity by calculating the slope of the tangent line at that point. Here's an example. I recommend pausing the video right now and drawing a picture of this example so you can write it down. What is the average velocity from time equals 0 seconds to time equals 8 seconds? To do this, we need to find the total distance, which is at about 128 meters forward. The total time is 8 seconds. The average velocity is always calculated using total displacement divided by total time. In this example, it's 128 divided by 8, which is 16 meters per second. We're going to find that the average velocity is completely different from the instantaneous velocity. So in the next step, we're going to look for what is the instantaneous velocity at time equals 8 seconds. To do this, we plot a tangent line to the graph at time equals 8 seconds. And we want to find the slope of this line. We pick 2 points on the line. I'll pick the time equals 8 seconds point, because we've already found that distance. And I'll pick time equals 6 seconds, because that's another nice spot to pick. The slope of this line is equal to y2 minus y1 over x2 minus x1. So the slope of the line is 128 meters for the top point minus 60 meters for the bottom point, divided by 8 seconds minus 6 seconds. The slope is equal to 34 meters per second. And since we're looking at velocity, this is going to be a forward direction. This is the instantaneous velocity at time equals 8 seconds. So the average velocity up to 8 seconds was 16 meters per second forward. The instantaneous velocity is 34 meters per second forward. These are two really different numbers. This is because the average velocity takes into account all the slower times that came before it. So as the curve increased in speed, the average velocity still took into account the slower speeds that were at the beginning. This is why it's so much lower at 16 meters per second than the instantaneous velocity. The instantaneous velocity at 34 meters per second is much larger because it's the exact velocity at that moment in time. So we'd expect it to be different. We're also going to look at what tangent lines mean in terms of velocity as a function of time graphs, or v versus t graphs. So if we look at a v versus t graph, at a graph that involves a linear shape and a curved shape, we recall that the linear graph means that we have a constant acceleration. And the slope of this linear graph is the acceleration of the object. The curved graph, or the quadratic shaped graph, tells us that we have changing acceleration. But we can still find the acceleration at a particular point by finding the slope of the tangent line. We would call this the instantaneous acceleration. The slope of the tangent line to a v versus t graph is the instantaneous acceleration. We're also going to look at areas for v versus t graphs, because these are actually also useful. So here's a simple v versus t graph with a linear shape. Now, a triangle is created if you look at the shape between the curve and the x-axis variable time. The area of this triangle is given by 1/2 base times height. We're not going to look at numbers, but let's just put the units in. meters per second times seconds. Since we have seconds on the bottom and seconds on the top, seconds cancels out and we're left with just meters, which is the unit of displacement. So using unit analysis, we can see that the area between the curve or the graph and the x-axis, which is time, on a v versus t graph gives you displacement. Underline between the curve and the x-axis. This is going to be really important later. Start with an example. Pause the video and draw a picture of this example and then continue. What is the displacement between time equals 0 and time equals 4 seconds on this v versus t graph? We start by realizing that there's several areas going on in this picture. We have two triangles and a rectangle. The total displacement will be the sum of the areas of these two triangles plus the area of the rectangle. The first triangle has a base of 2 and a height of 10. The second triangle has a base of 1 and a height of 5, and this rectangle has a length of 2 and a width of 5. The area of the first triangle is 1/2 base times height, which equals 1/2 2 times 10, which is equal to 10 meters. The second triangle has an area 1/2 base times height, which is 1/2 1 times 5, which is 2.5 meters. And the rectangle has an area length times width, which is 2 times 5 makes 10 meters. The total displacement is the sum of these three areas. 10 plus 2.5 plus 10 is 22.5 meters, which in SIGDIGS is 23 meters. Here's another example, and this example is going to include a negative area. In this graph, I want you to find what is the displacement between time equals 0 seconds and time equals 3 seconds. So remember that negative v means backwards velocity or backwards travel. So negative area doesn't actually mean negative. Negative area means backwards displacement. We're going to have two triangles. The first triangle is a positive area, and the second triangle is a smaller negative area below the x-axis. We add these two areas together, but make sure you include the negative for the velocity. So we have negative 2.5 as the height of, or it's negative 2.7 as the height of the second triangle, and 1 as its base. The area of the first triangle is 1/2 base times height, which is 1/2 2 times 6. This is 6 meters. The area of the second triangle is 1/2 base times height, which is 1/2 1 times negative 2.7. And it's important to realize that this negative 2.7 tells us that the object was moving backwards. So the answer is 1.35 meters, but this is negative or backwards. So when we combine these, 6 plus negative 1.35, we find that the displacement is 4.65 meters. In sig digs, that's 4.7 meters. And since it's positive, it's forward.